Okay. Today's and we will have two presentations. And the first is from Ruofan's work, Ruofan presentation. That's more to look more into how the humans and machines can cooperate with each other. And because in the future, in our course projects or in our experiment, we just train the models and verify as long as the model can fit well on the data set. However, in practice, when the model is deployed, it is quite possible that the model will go through a lot of unseen data. We've gone through a lot of unseen data, and we never expect their behaviors. And what the model can be, what the model can do with those unseen data, and how can we retrain the model to further improve and evolve the model, so that all is very practical and very interesting topics. So Ruofan will give us a presentation.
Hello. Today I will present the paper Towards Human-Machine Cooperation, Self-Supervised Sample Learning for Object Detection. This paper is published in CVPR. And the first three authors here. The first author is a postdoc from UCLA. Second author is now a computer vision researcher at Chen. Third author is a research associate from Sun Yat-sen University. Their background are all from computer vision. The problem for this paper is that this research is trying to address the problem active learning in object detection in self-supervised way. Here, self-supervised means we use the model to generate pseudo label for some of the data. Before diving into details, I want to do a big recap on active learning. So for normal supervised learning, given all the unlabeled data, humans need to go through all of them and label all of them and send to the model to train it. However, in active learning, we start from an initial small set of labeled data set to train the model, and the model selects some unlabeled data that it considers as informative. Humans only need to label those part of data. The process of training and selection goes iteratively until converge. In this process, humans only need to label partial data, not all the data, because of the additional selection process can filter out those uninformative data. So as you can see, the advantage of active learning is it's cost efficient because it saves manpower. In addition, if we want to deploy the model in the industry, then active learning is a more practical scenario because every day there will be huge amount of unlabeled and unclean data coming. It's not possible to go through all of them. That's about active learning. Because this paper is on object detection, so I will also briefly go over what is object detection. For the usual classification task, we only need to tell the class of the object, but not the position of it. On the other hand, object detection is more complicated. There might be multiple objects inside the same image, and I need to predict the precise location of that object and also the corresponding object class. In other words, object detection is equal to classification plus the bounding box regression. For object detection, the design of model architecture is also a little bit different from normal classification network because bounding box regression is a very challenging task. So one common architecture is called two-stage object detector. In the first stage, region proposal network can roughly propose some regions that are highly likely to contain an object. In the second stage, the box head will further adjust the position of regions and predict the class of it. Hello.
I'm listening. Please go on.
So yeah, this is the same slide as before. The problem is to use active learning in object detection in self-supervised way. One challenge here is in classification network, the definition of uncertainty is well studied. We can use entropy or top 1 minus top 2 confidence to quantify uncertainty.
Oh, by the way, the top 1 minus top 2 is there the literature's approach in the literatures, or you just borrow it out in our result?
It's called margin.
Okay.
Margin. Yeah.
Okay, it's called margin. Okay, so we do have something similar to some literature, right?
Yeah. Yeah, so the idea is just that those lying on the classification decision boundary are uncertain, so they are informative. We should select them to include them in our training to improve the performance of model. But it's just not clear how to quantify uncertainty in object detection because it has two goals. First one is classification, second one is regression. So we need to design some kind of uncertainty to incorporate those two tasks altogether.
Here I have a question. So for regressions, and how do we, when we have a confidence, when we have a classification, because we always have a score, the confidence score for us to decide whether it is uncertain. But for the box regressions, it's just we regret a value there, right? And how do we get a confidence for, or how do we have the uncertainty for these B-box or those box regression?
Yeah, that's the challenge, right? That's the challenge the paper wants to address.
Okay.
So the contributions of this paper is introducing a consistency measure to quantify uncertainty in bounding box prediction. The second contribution is it is trained in a self-supervised way. It leverages those low uncertainty or high confidence examples, while the existing work usually just discard them because they only select those high uncertainty examples.
Wait. So this one, previous one. So leverage, no, next one. Leverage high confidence examples. Okay, this is used for pseudocode, pseudo-label generation.
Yeah.
Okay, keep going on.
Oh, maybe if you see this picture, then it's clearer. This is the overall approach. So first, we start with a pool of unlabeled or partially labeled samples. Then we call the current object detector to predict some region proposals. After that, for each proposal, I compute the consistent score defined by the paper. For proposal with high consistency, then we kind of trust the model and then use the model's prediction as pseudo labels and append to training. For proposal with low consistency, we need to ask human to label them and append to training. So first, let's see how it defines.
But the problem is that, okay, so high confidence or the high consistency includes both the regressed box size and the label, predicted label, right?
So first, let's see how it defines.
So is there necessary to do this job because the model has already been very confident? The model has already been very confident, or
yeah,
okay,
because it's already been very confident, so we trust the model.
Yeah, we trust the model.
So we do not need to label them.
Yeah, but why bother to feed those samples into the model to retrain the model? So let me raise just a simple example here.
Because I think we always want more model or more data with labels.
Yeah, the point is here. So suppose the model is very confident on those giving the decision boundary.
Then this
So
paper
model-
does not consider the scenario which is wrong but high confidence.
No, this is not what I mean.
Hmm.
What I mean is that when we have a decision boundary, so those samples that have very high confidence, right? Because they are kind of far from the decision boundary, so they will have a high confidence. But think about it. So suppose we keep sampling this data. It's not very informative. And in that case, when we feed the model with those kind of the samples, it will be pull the model back here, right? It was
But according to their experiment, they claim that combining active learning with pseudo-labeling can achieve better performance than any of the individual of them. Yeah. So yeah, I think that.
The pseudo label, and also it need to make sure the pseudo label are kind of so the samples with pseudo label is supposed to be even or distributed evenly on different class, right? Otherwise,
they didn't
otherwise they will introduce the risk of overfitting, right? So just like
we don't know, but according to the results,
yeah,
it's
I
not
understand.
overfitting.
Yes. Suppose it is baseline, we definitely need to re-implement or take the code to see the details, right? So I'm talking about, so don't talk about experiment data now, because we would like to have a rationale and they would have insight into why this method will take effect. So here,
I think we shouldn't only sample those low consistency. This high consistency example might also be helpful.
okay. So is there any guidance for selecting the number of high confidence data, high confidence data and low confidence data? So for example, I add maybe 100. We add 100 low confidence data. So do we need to add maybe 200 or 100 high confidence data to balance it?
According to their experiment, they add more pseudo-label than active learning, pseudo-label samples than active learning samples. Now here you see the percentage. This percentage is with respect to the initial training set. And it's better than if we just, so here SSM means only pseudo-label, AL means only active learning.
Only pseudo-label. And is there any baseline for what if we get nothing?
Oh, it's 73.9.
73.9. Okay, let's go back here. So if we only do it's really weird because the annotation, there's no annotation, and it just add 300% means that it adds 3 times more than the training data. I didn't believe the result. How can we explain it? How did the author explain this? You can think about it. So assuming there's the board, just like what I said, there have a few samples here and there between the boundaries, and we repetitively add a large number of high confidence data. And how can it improve our classification?
It's basically, the more data you have, definitely you will increase the accuracy.
No, the data. So what if
It's like you increase your training set, then usually it will increase your accuracy, right?
So you just remove the noise in the data set. If you increase the data set, if there are more noise, then the model will have bad performance.
Yeah, it's something like this because this high confidence one can be said.
Think about it. The model before after learning is overfitting.
No, it's not overfitting. It's underfitting. It's underfitting because we start with a small training set, and like the rationale behind active learning is to label less data to achieve a better performance than looking at all the data.
No. From the very beginning, from the very beginning, there are very small number of data, and there's a large number of testing data. So it could be easier for the model to fit the training small number of training data well, right?
Yeah, and this is on testing. This MAP is on testing.
And how about this training data set?
Data report, because it's not useful because the training data set are different, right? After you add more samples, then training data set becomes different.
Okay, keep going on.
Okay. So it defines a consistency to quantify uncertainty. And the consistency is defined by cross-image validation. Given an unlabeled proposal, xi, then it is pasted onto another image, which is an annotated image without trace category. And then we feed the pasted image as well as the proposal xi into the model's box head to get the final reported box. If the final reported box locates close to the original yellow proposal and also with high classification confidence, then that proposal is consistent.
Then how do they select the baseline or the images to be pasted?
Random.
Okay.
For example, in the first row, the cow is pasted onto some random background, and then the final reported box still have high overlap with the original cow. So it's of high consistency compared to the second row. You see the dog is pasted onto some other images, and then the red boxes move a lot. This is a low consistency example. So as I mentioned, the second contribution is this paper utilized the low uncertainty examples. So it just trusts the prediction from model for those high consistency proposals.
And how about the classification?
This consistency score is defined to include both classification and also the overlap. The formula is like this. So given xi, it randomly choose 5 other images to be pasted to, and then let's use xp to denote the pasted proposal. Then we feed the pasted proposal as input to object detector's box head, which is the second stage of object detector. Then the consistency is measured in terms of the bounding box IOU intersection over union, which measures the overlap with respect to the original xi. And also the confidence.
Here, can you remind me about the box head? The box head is the RPN.
Like I said, there's 2 stages, right? There's 2 stages in object detector. So it's possible to just feed an image into the region proposal, then get a prediction, but it's also possible to feed an image with its proposals into the box head to get its prediction. So It's like we're only using the second stage of the detector because we already got the proposal, right? So
that means we are just using this one and this one.
yeah.
Keep going on.
Oh, hi. Can you explain IOU a bit more?
Oh, it's intersection over union. So for example, given two box 1 and box 2, then the intersection region is just this part, right? Union region is just this big thing. So if this IOU is high, that means these two boxes are highly overlapped.
Oh. So okay.
So
are you putting the pasted image in order to overlap with oh, are you saying that you paste the image to different image and then do the prediction, and if all of them have a consistency, then that means the model is very confident with its results. Is that? Oh, okay.
So for example, we paste the original proposal xi onto two different images. Then in image 1, we get the final reported box, which is the red one. And then we measure the IOU between the red one and the purple one. If it's high, then it means consistent. We also compute the classification confidence for this newly pasted proposal, which is 0.8. And then we do a thresholding on the IOU. The thresholding is just, if it is above 0.5, then it's just 1. So the consistency of this particular pasted proposal is equal to 0.8. When the proposal is pasted onto the second image here, you can see the
Is that 0.5?
Yeah. The 0.5 is the threshold they use in the paper.
Okay.
And you can see the IOU is only 0.3. So after applying thresholding, is equal to 0. So even if it has a classification confidence here, which is non-zero, then the final multiplication is still 0. So the consistency for this proposal is simply taking the average between 0.8 and 0, which is 0.4. Yeah. And in their experiment, they random select 5 images to be pasted instead of 2. And then after that, they just take the average consistency.
And what about their pasted positions, random positions there?
Yeah, it can be random. Like in this example, you see it can be random.
Okay.
Okay. Step 2 is for those high consistency proposals, we get the pseudo labels. The formula looks complicated, but the basic idea is we just try to assign one class and only one class to that proposal, which minimize the cross entropy loss. So in other words, we just assign the most probable class for those.
Sorry, I missed it here. So when
Yeah,
we
no,
have
because now you got the consistency score, right? So you can just rank, then get those high consistency proposals. For those high consistency proposals, as I mentioned, we use pseudo label from the model. So how do they assign the pseudo label? Is they just assign Y such that each proposal only has one class assignment, and this assignment can make the classification loss the lowest.
I didn't get it.
Huh?
Where is it? Where is the classification loss?
The classification loss is this L.
So the point is assign the pseudo label.
Yeah. So now we are assigning the pseudo label. Then how do we assign? We just assign the most probable one, right? Which minimize the classification loss.
So here it will have more. Let me look at the formula. Let me look at the formula again.
Actually, you don't need to, because this formula looks really daunting. But the basic idea is, yeah, it's simple. So
The
if
pseudo
you
label
look
yi.
at the idea, it's very
Why the
difficult.
yi it has a dimension of -1 to 1?
Why could be positive and negative. If we have M class, then I have my. And each y can be positive and negative. Positive means belongs to that class. Negative means not belong to that class. And this constraint just means we only assign it to one class.
Okay, let me look at the last two lines. And vi is
It's an alternative function, which means we only look at some specific class. Because you don't need to minimize the class which is highly unlikely. So we only need to minimize the loss, which for the most likely class.
I'm still digesting the formula here. The pseudo label.
But do you understand the idea here? Right.
I'm
going to assign.
I'm aligning your idea with the formula. For here, the pseudocode is a pseudocode.
For example, if you forget about this VI, right, then this is just this loss is just the binary cross entropy loss summing over all class. Because the way they design their model is a bit weird. When they train the classifier, they didn't train the multi-class classifier. They train a multiple binary class classifier. So like for each class, they have a binary classifier. So that's why they will have M binary cross entropy loss.
And where does the pseudocode play a role?
Pseudo label is just yi. Pseudo label is just yi. Is how do we label those proposals?
So J means the number of the M proposal, right?
M means the number of class.
The number of classes. And I means the individual.
I means the xi proposal, and J means the J's class.
I means I's proposal. So given images, we have multiple proposals, and each proposal will have a class.
Mm.
And here we would like to minimize the VI times J means the class. So for each proposal,
For each proposal, we are finding an assignment of class, right? We are looking for some class assignment.
this is the class, and this is the proposal P.
Yeah. Yi is the pseudo label we give to xi, and we want this pseudo label to minimize the classification loss. In other words, we want to assign the most probable class to that proposal.
But this proposal has already been selected. Can we go back to the first step?
This is unlabeled data, right? All these proposals are labeled.
Yeah, I know. So the idea is that we already have predictions. We would like to assign the label according to the prediction.
Yeah. That's the idea.
And but the point is that we already, based on the prediction consistency score, we already have assigned the prediction, right?
After the prediction, you only have whether you need to label.
Oh, can you go back to the next slide? Next slide. Okay. Here we already have this one, right? So given xi, we already have this point. Right. We already have this point. So in that case, so xi is images, and
proposal.
xi is the proposal. W is
weight.
The weights, the classification weights. Okay, let's go back. Next one. So error here. Do you have any definition of error?
L is the binary cross entropy loss for class J. And for proposal xi.
For fxi, so fxi can provide a confidence.
I think here is it just means that we only look at those loss that are lower than some threshold, and this threshold is this f.
This f is calculated by previous calculation. So given this xi,
you
we
can
have
think
a confidence.
of it as a fixed number. You can think of it as a threshold. It's just that the threshold is dynamic for each proposal xi.
Yes.
And then we apply the thresholding on each class. So for some of the class, if their loss is really high, then this VI is equal to 0, right? So if their loss is really high, we don't try to minimize them because you think it's unlikely. Yeah.
Given this proposal, and this is this function returns the class of this proposal. And we only looking to what means.
If you forget about this VI, then this is just a summation of binary cross entropy loss, right, over all classes, right?
And where's the label? Where's the label of this xi?
Oh, here. Here for each yi, you can just get the binary cross entropy loss, right?
Which yi and y.
Yeah.
Cross entropy loss here. Okay, so when we add a bi, it actually means the proposal.
Look at some of the class
Can I ask a question? What's F mean? F.
F is our previous calculated consistency, but for now you can just treat it as an arbitrary threshold.
No, Xiaoling asking about the, for example, here, I think there's a logical gap between this one and the slide. So let me,
I think it's not very important to look at the details in this formula because the idea you understand, right? You just assign yi, which is most probable. Simple, right?
That's very clear, but I think the details matters here. And also I'm trying to look into, so I'm keeping ask questions. So, so some giving images, some proposal will be labeled, but some proposal will not. Am I right? So it means that this approach will introduce a mislabel, right?
What do you mean?
I mean that suppose their images, there's supposed to be 10 proposals there, but it will only label 5 of them, and the rest of them are missed.
This selection is based on proposal, not based on images. So maybe.
Of course, the proposal is on the images. So
yeah,
images,
but
they have 10 proposals.
They rank the, like they compute the consistency and rank.
Yes, they only
based on proposal.
They only have pseudo labels on the proposal, which has high consistency, right?
Yeah.
So the answer is yes. So given the images, there's supposed to be 10 proposals, but given their pseudo labels, they only assign pseudo labels for 5 of them. Even all of the pseudo labels are correct. Okay. So
I have a question. So this is this a multi-label model? It means for each proposal, we can assign multiple labels to it.
Each proposal
No, but the model is designed in that way, such that each classifies one versus the rest. But when you do this pseudo label assignment, you see there's a constraint, so it could only be assigned to one class, actually.
One class, but here.
Does that mean because here you sum from 1 to m, but only one j.
Only one yj is equal to 1. The other are equal to -1. Yeah. So that's what the constraint means.
Oh, okay.
So here we got the label 1, 2, and the classes. For every classes,
so this formula just returns back the loss for one label, right?
For each
LJ.
Oh, LJ is for one class label.
Yeah, just one, right?
LJ is the class for one. Since the J sums and classes. And do we need to sign up for the? So this is for this one just for one proposal.
Yeah.
This one for one proposal. And sum together. And giving this y. And giving this y. J together so smaller than 2. And how can you predict this, interpret these equations?
I have mentioned you just have one yij equal to 1, the other one equal to -1. In other words, you only assign one class to that proposal. That's what the constraint means here. Because if you have
suppose we have 10 classes.
2 yij equal to 1, then your sum is larger than 2, right? So you can only have one ij equal to 1.
Okay, so overall, the idea is that we just assign labels to each proposals and assign labels to those confident proposals. Right, so that is an overall idea.
Yeah, that's the overall idea. But if you see the formula, it's quite confusing. Yeah.
So I have questions for you here. If given images, there have some label which is missed, and what will be the consequence for the object detection model? Because it only looks into the confident proposal, right?
I think they will kind of ignore the rest of boxes reported by the model. And when it penalizes the loss, it is based on each proposal, right? So I think it's okay to mislabel to do not label some of the objects inside an image, because when object detector calculates the loss, it will not penalize on that.
Well, the model will remember the features, right? So no, so you say it will not penalize. It will not penalize the missing label. But for example, given the object detection model, right? So it will have prediction on every grade. Am I right? So in this case,
no. For two-stage, it will not. For two-stage, you RPL. In RPL, you will have some proposal, but it's not on every grade. You will get maybe 1,000 proposal, but it's not on every grade.
No. You didn't get on me. So I'm asking that their approach is actually they work fine because they do not train the RPN proposal, the proposal network, right? There's a network to generate proposals. So this proposal will be the network generating proposals be trained based on new data?
Yes.
Then there will be problem, right? So since that given an arbitrary images, we need to generate a proposal, right? That means given each grade, anyway, each grade they will have a proposal there. But given certain feature, they're supposed to have an object, but actually it's not labeled there. In the model will be reinforced to miss or ignore certain object.
I will go back and look at the loss.
You can go to the previous one. Go to the previous one. Go to the previous page. So you get my point, right?
Yeah.
So can you go back to the previous one? So I hope that everyone can understand, not like you, but Shawnee just can understand my point. Previous one. Further previous.
But I didn't put the loss for training here.
And the previous one, I think the loss, yeah, I guess it is just using the original loss, not the new loss, right? The previous one, the further previous, and the further previous object detection. I didn't need to know. Yeah, that's this part. So once we have new images here, so it will passing this network and this network, right? And this part will still be learned.
I still think that for the extra proposals here, if it does not match to any ground truth, maybe here is the ground truth, that there's no penalty on this proposal.
No, I'm saying the missing labels.
Yeah. So if there should be a ground truth, but you didn't label it, and the model predict that there's a object, but because you didn't label it, so when calculate the loss, actually each proposal will be matched to a ground truth if it is overlap. If it does not match to a ground truth, then there's no penalty.
Yeah, it's no penalty in the loss function.
Yeah.
It's
So
not, there's
it
no
will
pen-
not affect. Yeah, it will not affect.
It will affect in the.
Why it will affect? Because there's
will-
no penalty, so it's okay that you predict an extra here.
No, assuming that the model predicts some proposal here, and assuming it's correct, but now there's no label, then the loss function will tell us that the point there should not propose
If there's no label, then it does not match to any ground truth, then there's no loss.
No. The point is that when we train the region proposal network,
Yeah.
and the model will actually randomly propose at the very beginning.
Yeah, the model will then
Mm.
match each proposal to a ground truth.
Yes.
If a proposal cannot be matched to any ground truth, it just ignore. It does not have additional loss on those extra reported regions. That's why I say it's okay to.
Okay,
Yeah.
please repeat your last sentence, and let's redigest your point. So if a proposal cannot be
overlapped with any of your ground truth label,
yeah,
then in the last term, it just ignored that proposal. It does not put extra penalty.
So if that is case, given images, they were supposed to be multiple noise proposal.
Yeah.
Is that fine?
Yeah.
It's not fine. It's not fine. So just
noisy you always have. You will have many noisy proposals if you only look at the output from region proposal network without any threshold. You will expect 1,000 region proposals.
So the second question is that for each proposal, will there be a measurement called objectiveness? For each proposal, will there be a value of objectiveness? Because for YOLO, there is an objectiveness values. So when we are calculating the score confidence, it will be the objectiveness score of a proposal times the confidence of another a class confidence, right? So there's supposed to be overall threshold, and for your fast RTN, is there something like that?
I forget. I need to revisit the loss.
Yeah, so there's a tricky part. So my point is that overall, so there might be have some trick to address these problems. But there the problem is that if we because for the region proposal network, there's supposed to be a lot of grade, right? There's supposed to be a lot of grade. And for each grade, if it misreported a proposal, the loss functions must be the way to suppress such a proposal. Otherwise, it will be so many proposals. There, of course, each proposal, if there's no objectiveness score, it just times the classification confidence.
Why not we organize another sharing session on two-stage object detector? I think we need to review, right?
Yeah, we somehow need to review, but here I just have a concern is that if we feed the model with the images, we feed the model with images with missing labels, it may cause some negative performance. I just criticize on this point. Criticize the approach on this point, but maybe they have a tricky part to address these problems. But I do have such a concern there.
In my opinion, maybe no, but yeah, I need to look at the loss again.
And missing the label is actually equivalent to having some additional random proposal, right? A random label.
I think we just stop the discussion here because I think we need to go back to the loss design, right?
Okay, so do you have loss design here?
No, I don't have. Let's, yeah.
Okay.
And step 3 is that for those low consistency proposals, they will just send to human, and human will label them. Step 4 is we update the label dataset and optimize W in terms of classification loss and regression loss. And in their experiment, the evaluation matrix is the MAP at LU threshold equal to.
Sorry, I just have a comment on the previous slide.
Mm.
So that's about your design the regression loss, right? Once we have the regression loss, it's actually about the regional box, right?
Regression loss is on the final reported. So here we are training the object detector.
Yes, I'm talking about our detector. So once we have a regional, we have a box, we will have a regression loss, right? So, but here it's about it's more like the fast RCN model, right? Fast, not faster. It's actually the fast RCN loss there. Okay. So this is the fast RCN, not the RPN. It's not RPN loss.
The fast RCN also have RPN.
No, fast RCN just takes the proposal reported by by RPN. The faster RCN model. Faster RCN model.
Faster. This is a picture of fast RCN.
Yeah, so this is the fast RCN, and this is RPN, and the whole network called faster RCN. So I'm talking about what the regression loss is on this fast RCN, right? And in that case, I do believe that if we train this RPN network, we do have something like the objectiveness. Otherwise, it will report all the proposals. But for the RPN, it will just report a limited number of the proposals and feeding to fast RCN. This is fast RCN, and this is RPN. And the whole network is called a faster RCN. Right, and the regression. So I believe that if they retrain the model, and if they do not modify the loss, they will have the consequence, despite their experiment data looks very promising.
I still think fast RCN has
Right. If the regression is on a fast RCN, okay, let's
fast
go.
RCN, it still has something like region proposal.
No, fast RCN just adjusts the proposal reported by RPN. I think I read the paper. I think I read the paper carefully, so no worry. I think what I mean is correct. I assume that what I say is correct. So let's keep going on.
So the model they use is fast RCN and RFCN. The paper's approach is denoted as FRCN plus hours or RFCN plus hours. They also did some ablation study, means they only use
what is
pseudo label.
RFCN? What is RFCN?
RFCN is another model. I didn't look at the details. Okay. It's another two-stage detector. And FRCN AL or RFCN AL is only active learning proposal, not the pseudo label proposal. So they find that hours can achieve same MAP at 30% of annotated examples with other kind of baselines. which is trained on 60% of annotated examples. And in the Augmentation study, they evaluate the performance of using those pseudo-labeled data. They compared against their previous work, and they find their MAP is superior. They also compared the pseudo-label with other kind of random data annotation technique to generate pseudo-label samples, and their MAP are higher. So here, they claim that if we combine active learning and self-supervised mining, then it's better than either active learning or self-supervised mining.
SSM is called, what's the full name of SSM?
Self-supervised mining.
Okay.
So the takeaway from this paper is they use cross-image pasting to evaluate the consistency. And they divide the model training into two branches. The first branch is we trust the pseudo label from model when consistency is high. Otherwise, we query the label when consistency is low. Yeah.
Yeah, this is, despite there is some debate and argument, I think Ruofan did a very good job in presenting this paper. But maybe we need to take care because after the CCS simulations, and you were focused on active learning, So we're going to see, especially in the object detection, because for the CCS paper, for CCS submissions and the use mix papers, we are train the models iteratively, repetitively. So I assume that we have already got the good experience of adjusting the model. So in this case, we need to have some deep insight. We know already have some intuitive feelings for the programs, but we do need to think critically and have some insight about how this approach. For example, giving the entropy-based approach or the entropy-based approach are going to remove the false positive, right? It's more like to improve the precisions. But how about to address and also for the self-supervised learning or active learnings, it is still looking to the precision, right? To improve the confidence of the precisions. It may even makes the problem of the low recall even severe, because when labeling a smaller number of labels proposals, it means that when the image has misreported some things, it is just missing. And how do we address the problems of missing proposal? I think that will be a very interesting area for us to explore. Okay, the next one, how about Yufan?
Oh, hello. So today our paper is exploring simple Siamese representation learning. It's a paper from CVPR 2020. The others of this paper is Chen and He Kaiming, and they are the He Kaiming is very famous because he invented the ResNet, and he has many best papers in CVPR and ICCV. And Chen is from Zhejiang University for undergraduate and CMU PhD, and now they are all in Facebook AI research. Their research interest is machine learning and computer vision. So first, we need to understand what is Siamese. Siamese actually is the old name of Thailand. The Asian Thailand is famous for the Siamese cat. In Chinese, it means 新罗猫. But in 19th century, Siamese twins. Let me use some like this. Okay, so Siamese twins are born in Thailand, are very famous all around the world. So day by day, the Siamese has a new meaning, the conjoined twins. And what is the Siamese network? The Siamese network has two input and two network to receive the input and one to finally compute the loss. The two network always share the same weights, and if the input is two sentence, the network may be the two LSTM. If the two input is two pictures, maybe the network will be the two CNN. And if you use the different neural network, it's okay. It's called pseudo Siamese network. There's no share weights. For example, one LSTM and one other CN. That means you get one input is a picture and another is the sentence. You want to measure the similarity of one picture and one sentence. So you use a different neural network. And the history of Siamese signature goes back to the NIPS 1993. That paper called signature verification using a Siamese time delay neural network. This neural network are similar to CN, and it's used to compare the two pictures of signature to check whether they are same or not. So why use the Siamese neural network? The intuition behind it is that it wants to compare the similarity of the two input. You can regard the two neural network respectively maps the input to a new space, which forms the representation in the new space. Through the calculation of the loss, the similarity of the two input is evaluated. And for more detailed analysis, we can go further. For the loss function, originally we use the constrictive loss.
Constructive. Constructive. It's constructive. There's a typo there.
But it used the constrictive.
Constrictive. Okay, so let me check it. So you keep going.
A bit different name. And look at the formula. If y equals to y, it means the picture are similar. Then the loss becomes just the formal part. The formal part. Yeah. So you want to minimize the distance between the similar input. And if y equals to 0, that means the input is not the similar. So you just look at the later part. You want to maximize the distance between the two input. Okay, so now we just have a brief understanding of Siamese network. We now have an understanding of what is representation learning. So just Ruofan just mentioned the self-supervised learning. So actually it is a bit difficult to clarify the different terminology. We also, we are very familiar with the supervised learning and unsupervised learning. So we look at the semi-supervised learning. It means that large data with small part of them is labeled. It can be, there are many subclass of the semi-supervised learning. We just talk about the active learning because it is have an expert to label the data, label the ambiguous data, so it calls active learning. So for some like transducive learning, so that means the unlabeled data is the testing data. And the inductive learning, like the unlabeled data is not the testing data.
Not the test data, that means the training data.
Yes.
Not testing.
Inductive learning. So yes, it's true.
So the methodology reported by Ruofan just now can be considered as inductive learning.
Yeah, it is a kind of inductive learning if you use this classification method. Yeah, another semi-supervised learning is distant supervised learning. It is very popular in natural language processing. So add this supervised learning in this because maybe you are not familiar with it. For example, if you have a fact, this is the labeled data. Jobs create the apple. Now you want to train the relation of created. Then you now regard all the sentence with jobs and apple as the labeled data. that means for example, in the data set, you also have a sentence like Jobs is the founder of the Apple. This is unlabeled. Is the founder of the Apple. This is unlabeled, but you find that this sentence also contains two words, contains the entity of Jobs and Apples. So you just think this is also labeled data of created. So you can use this example to train on the created relation. But there is a very typical noise that you maybe in the data set is that there is also a sentence like Jobs eat the apple. So this sentence may also exist, but it's not the relation of created. So this is a noise of this this method. And so for today's topic is the self-supervised learning. It's actually very popular in today's machine learning. For the model architecture workflow of the self-supervised learning is follows. You input the image and automated the labels and then train the representations of the picture and transfer learning for the downstream task. The self-supervised learning is very popular. Yan Luken once said, if intelligence is a cake, the bulk of the cake is self-supervised learning. So it is very important for the machine learning. And a popular model like word-to-vector, GLOV, GPT, and BERT, they are also borrowed the idea of self-supervised learning. And in computer vision, I'm not familiar with this field. Maybe the colorization, I just searched that the colorization is one of the supervised learning method. Like you want to colorize the picture and you just grade the colored picture and then retrain it. Maybe you can, if you are interested, you can have a further reading on this topic. And what is
so we can summarize. As long as it requires will require less manual effort to label the data, they can be considered as a self-supervised learning. And for your colorizations, can it be considered self-supervised learning? Because we just inverse the color image into a gray images, but the label is just there, right? So according to definitions, self-supervised learning are the process where the data set, only a portion of the data set, training data set has labels, right? And in your, according to this definition, and in your description or introductions of the colorization, every training data set has a color label, right?
Yeah.
And
gray picture has a color picture. So you can train the colorization process using this data set.
And here, all the data has label. So why it was called a self-supervised learning?
Oh, pardon, please. So you mean all the label are just
are there. All the labels are there. So we for Ruofan's approach, a lot of data, for example, it attached pseudo labels to some samples because the model is, we know the model is very confident to predicting very confident in predicting those samples. So definitely that's self-supervised learning. And in this case, in your case about colorization, every sample has its labels. But there the tricky part is that this label does not require manual effort. We can just using an automatic approach to label the grayscale picture. But why this called supervised learning?
Yeah, so we go back to the workflow. You can see that the supervised learning actually learn a representation. So this representation actually is the goal of the self-supervised learning. Then use the representation for the following downstream task. Okay, so for the colorization task, you have the clear label and the clear data set. So you actually train the learned target train, like maybe
But the supervised learning do the same, right? Suppose I just change this one, remove the self-supervised into the supervised. It does the same, right?
Yeah, but because manual labeling is costly, so we need there's not much data set that is labeling.
Okay, keep going. I think there's no need to linger around the definition stuff. We somehow get a feeling of self-supervised learning. Let's keep going.
Okay, so now is the constrictive learning. So constrictive learning actually a subclass of self-supervised learning. Self-supervised can be broken down into two classes. One is generative or predictive process. The main difference is that the laws mentioned in the output space. For example, the autoencoder. Yeah, I think you can understand because the loss of the loss in the autoencoder models, it's mentioned in the output space. It is mentioned in the final layers, and for the contrastive learning, actually the loss mentioned in the representation space. So it's quite different. Maybe you feel a bit confused, so we will go further to introduce the constrictive learning. And typically, we use Siamese network as the constrictive learning neural network architecture because you can see it is very similar to the Siamese architecture. Okay. So now we have clarified the terminology and clarify what is self-supervised learning and the constrictive learning. So we now focus on the paper. It has two contributions. First, comparison with other models. This is very in Chinese like 砸别人的饭碗. That means it just says simple Siamese network also works very well. So many other researchers want to make it more complex, and write papers. So it's just compare with other models. A simple network also can learn meaningful representations. And so why it's simple Siamese network also works. So he provide a hypothesis on the implication of stop gradients because he thinks the stop gradients mechanism is very important. So here we have a very quick view of the simple network. We can compare with the very complex network. It also works quite well in the task. Okay, so we first compare to other models. To understand the comparison, we needed to introduce other papers focus and points. The first is the CVPR. It is published in ICML 2020, and the performance you can see that not only improve upon the previous state of art self-supervised learning method, but also even better than the supervised method when scaling up the parameters. And here is the example. I just show you an example of CVPR. I searched an example on the website. So now the question is match the correct animal. You got 4 examples in the data set, and one you want to choose which is the most similar almost similar pictures. The problem formulation is that you first need similar and different examples because you want to train the model. Secondly, you want to have a representation model because you want to represent the image to a certain vector. Third, you need to have a similarity function to measure the similarity of different pictures. So how the CMCR framework works, here is the framework. For the first part, how to get the training data set of different and similar, it just use the data augmentation. I'm not familiar with the data augmentation in computer vision. From my understanding, it's just like spin the picture or color the picture or something like this. And for the data augmentation, in details, the SEMI-CLR use the very large batch size of more than 8,000. For easy representation, we just use two batch size. And first is the data augmentation. We just applies a very here is a very random augmentation. Then for each image in this batch, then he transformed it to 4 total images because it used the 2 data augmentation, and now 2 by 2 gets the 4 image in 1 batch size. Actually, you must remember that actually it used a very large batch size because there is some question if you use the small batch size we will talk about later. And then we get the representation. Now we use the very typical encoder resonate architecture to get the representation of picture. Then we get a hidden layer. We get a hidden layer of like 2048 dimension vector. So after this, we now going to the projection head because you now want to have some latent vector, latent information of the picture. Now the projection head used by CMCR is dense, ILU and dense. Then it maximize the similarity of the 2 latent vectors. So I think it's just follow the typical Siamese neural network.
So it's just the trend similarity based on data augmentation, right?
Yeah. Based on the data augmentation.
But in some Siamese model, it will always label. So one of the most popular application of Siamese model is called the face recognition. So just giving images of you and other images, or for example, giving images of your identity card or a passport, and then you have an arbitrary of your images. We're going to compare whether 2 faces are similar or not. So in this case, we somehow not only for augmentation, but also for collect several of the faces, several faces of the same people and train a model. That is also possible.
Yeah. Actually, so the main purpose is to train the resonate encoder to get a better representation for the downstream task. Okay, so do you have any more question for the CMCR model? For the similarity, it's just to use the cosine. He used the cosine similarity, not the constrictive loss. He used the cosine similarity, and here is the loss, how to compute the loss function. It's not important. Okay, so now we goes back to the CMCR. Oh, actually, it's very interesting because for this task, it has like 4 comparison, and each paper is finished by very famous people. The first is the Hinton, and the second paper we will talk about later is from the DeepMind. The first is from the Google, and today's paper is from Facebook AI. So I think this area is very, there contains much debate on the on the network nowadays. So if you are interested, you can see the history of this very useful network. Okay, now we look at the algorithm. Okay, so we now look at the algorithm of the CMCR. First, it has fixed the batch size, the constant tau, and the encoder F and G, and the augmentation function tau. So it first have the augmentation get the 2 picture T and T prime, and then he just feed into the representation module and the projection module to get the corresponding latent vector Z. Then after getting the latent vector Z, he used the pairwise similarity. I just talk about actually the cosine similarity, and compute the loss using the some function. Here is not important because it just follows the typical loss function. And then finally, he gets a very better encoder. And
okay. Throw away G.
Yeah.
What is G?
Yeah, it is 2. There are 2 encoder because there are 2 neural network. Remember, there's 2 neural that share some simple, share the same weights for the Siamese neural network.
Sorry, I forgot your point. So let me ask one by one. So can you distinguish the representation and projection? And more specifically in F and G. So you have you got a representation first, then you have the projection first, second, right?
Yes.
And how to distinguish the representation and projection?
Yeah, the representation is used for the downstream task. Why does need a projection? Because in the paper it said we needed to, get the latent meaning of the picture. So just like the bird or the other self-supervised method, they all have a projection layer. That means after you get the representation of word, they projection to a certain space and then compute the loss.
So can I look at the loss? When we were at the loss of I and J, okay, but the projection actually included the information of the representation layer, right? So the final layer, the loss is add on the Z, add the projection result. Am I right? Right. So for now, you can see the S is calculated here, and it's just work on the Z. Okay.
Yeah.
Let me see about the presentation layer.
It's just the typical architecture.
But for our single-tail projects, we only look into the representation layer, and that's all. We do not look into the projection. Maybe projection can be used for. Okay, please go on.
Yeah, I will talk about projection later. There's more thing about the projection. So now we talk about the BYOL. It is published by DeepMind, and this picture is very interesting because we just have a picture before. We can just remind you, yeah, just like this picture. Here, it just removes the, performance that's better than it. So now for this picture, it just shows that actually the CMCR is not very good actually, is here. And the BYOL is much better than CMCR. It is also published in SLM 2020. Okay, so the methodology, so the difference between the two is that it has one more thing on here. So besides the projection, it also add one more layer called prediction. Okay, so let's focus. Let's just introduce at the start. First, we input two images.
This model becomes more complicated, right? So it becomes more we still need to design the prediction task.
Yeah. So you can see that the architecture become more complex. But today's our paper said, oh no, simple is also okay. So you need to understand why it's complex and then why you can just use simple.
But for Ruofan there.
Hmm?
So in our Siamese model, when we train a Siamese model to compare logo, actually we do have a prediction task, like the boil, right? If we just train a Siamese model, the network performance will not generalize well, right? And we first pre-train a model with the prediction task. And after that, we simply, actually, we not train the Siamese model at all, right? We just train a representations with classification and compare them. Okay. Keep going on.
So now there are two parts. One is online part, one is target part, online part and the target part. And on the online part, it adds one more prediction layer and then use the output of the prediction layer to compute the loss. So now he used the prediction layers. That means Q, theta, Z, theta to compute the loss. Okay, so then for the target part, it's just a stop gradient. Here, just a stop gradient. So that means it didn't compute here, compute the loss here. And which means they do not use the gradient to update the parameter of target. Okay, so now this neural network is not updated by the gradient. It's updated by the momentum. It is a very typical mechanism in machine learning. It's called momentum. You just
okay, but the loss here, so given the prediction, the loss is only updated on the online branch.
Yeah.
And is there any loss on the representation and the projection?
No. The gradient also just if you compute the loss, you still need the Z prime.
Yeah, I understand it. But the weights along the red part or the pink, the target branch are not updated anymore.
Yeah, the parameter of the target branch is updated by the momentum mechanism here. I just here use the constant tau, and so you can see it's just like how to say, just fix some original parameter and update some new parameter to.
But if the gradient has stopped, it's supposed to be 0. And where does he get the initial momentum?
You mean the initial parameter?
Initial gradients, right?
What's the initial?
So when you talk about
target part.
Let me look at it. Your formula. Theta is the weights, or am I right?
Yeah.
Theta is the weights or of the target branch.
Oh no, theta is the weight of the online part. Here is the theta.
Okay. And what about the theta of the? By the way, does these two share the same weights?
No, it's not, because we now use the momentum to update the
momentum. The momentum of the online branch.
Momentum is the mechanism. Actually, that's just add one constant to the.
I understand what is momentum. Momentum is that for example, we calculate the gradient in these directions, but we're now in the previous iteration, the gradient is like this. So we use the momentum to combine these two gradients and have a new gradient. This new gradient regards both the existing gradient and the previous gradient, and that is momentum, right? So
bit different in this paper. It's just here. It's just when updates the parameter of target branch, he used something like momentum to update the parameter. Here is the formula.
yeah, I'm thinking about that. Let me look at the loss. This loss is, can I read about this loss? The loss theta and the eta or sigma.
Yeah.
Theta Q is the predictions and a minus Z primes.
That's a compare the similarity of these two vectors. One is the prediction layer output, and one is the projection layer.
Okay, why they can compare the prediction layout and the projection layout? Projection.
Yeah, because they said that after the prediction, this Z theta map to a new space that more more like map to the space that's similar to the target branch, because the two branch has different parameter. That means they map the picture to different space. So we needed to add one more prediction layer to map to the same space. Could you understand this? Yeah.
Why, giving the original projections and giving the original projection layer, why they were conformed? Why they will be in different space? They're supposed to be in the same space, right?
No, they will be in different space because the parameter is different. The parameter is different because now they don't share the same.
But the parameters are always different.
What?
The parameters, even you're using momentum, the parameters is still different. Right.
Yeah. Now the parameter is different. So.
Oh, by the way, so here T and T prime are actually two transformation, right?
Yeah.
Two different transformation. So the architecture between V, Y, and Z are the same. I mean, architecture, when we initialize the architecture, they're exactly the same. Yeah. Right, the architecture. And it introduced one more prediction. And given these predictions, it's going to compare projection and I just feel a little weird. And why I still didn't get why we need a prediction. And this prediction is supposed to be have exactly the same dimension of D prime. Right, the Q should have exactly the same value as D prime.
Yeah, for my understanding, because the parameter is different, so the projection layer maps the picture to different space. So we need a more layer called prediction to map the Z theta to the same space with the Z epsilon.
It is a little weird.
Yeah, but it just use this mechanism.
Okay, so when we have a loss function, I think this loss function will be updated weights from Z to Z prime, from SG Z prime. So that is what is this SG Z prime means?
Just I also don't know. Actually, SG means stop gradient. So I also don't know why it is a stop gradient Z epsilon prime. I also don't know this, why he used this. Because in the loss function, it just use the Z epsilon prime, not use the SG Z epsilon prime. So follow the loss function, I think he just use here. Just use the projection layer output.
Okay. Keep going.
So the final loss is just a conversion the T and the T prime. That means you just input the T prime here and input the T here, and get another loss and just add them to compare the similarity of two pictures. Okay. So we go through the, now we look at the algorithm. Here, maybe it is more clear. First is the data set and the data augmentation, and then is the parameter in the online part, online branch, and the parameter on the target branch and the optimizer, and the steps and the batch size. Here is the momentum parameter and the learning rate. So after we sample the batch of n images, we first do the data augmentation. Here you can also regard this as a transformation, and then get the latent representation, latent vector of picture Z1 and Z2, and the latent vector Z'1 and Z'2. Here, I think you can understand because I said that is a conversion. So he just computed twice. Let me emphasize. After compute the t and the t prime, he will convert the t and the p. That means now he input the t prime here and the t here. So he just computed twice.
Okay, let's skip this one, and I think it's really clear about the algorithms. So just select the batch and apply the transformations, and just essentially this algorithm just represents the semantics of the previous one, right? The previous image.
Yeah. Okay. So now we because the time limit, so I didn't look at this part. And if you, because this is a bit different, he added some new technologies. I also very not familiar with it. So if you are interested, you can look at this. So we can compare with the different architecture and our simple architecture. You can see that we just remove the first thing is that stop gradient. Here is the gradient. So we just remove this. And another part is that we don't use the negative sample. We don't count the dissimilarity like this and this. And we don't need to use the momentum. We don't need to have the momentum. We just share the same weight of two encoder. The two encoder just have the same weight. It's okay. So the simple Siamese is just simplifies the semi-CLR and the BYOL. So let me go through the architecture of simple Siamese. We can look at the pseudocode. It just first have the augmentation and the projection and the prediction very similar. And then he compute the loss. Here is a bit different because this is how to compute the loss. Here he first stops the gradient. That means here is the Z2. Z2 has no gradient. Let me see.
Let's keep about the specific architecture. Let's go through your takeaway about the paper. So I think we can skip the detailed architecture. So what's the point of this paper?
Oh, okay. So after the experiment, it shows that stop gradients is important in the architecture. If without the stop gradients, the training loss will continue to the -1 because it's just a model collapse. And it feels the analysis the standard loss, and it shows that if without the stop gradient, it's always 0. That means the representation is the same because when input anything, the result is also the same representation. That means the model collapse. And for the KN accuracy, it is a method to evaluate the self-supervised learning method, you can see that when without the stop gradient, it is just a 0, and if you use the stop gradient, it's better. So that means stop gradient is very important in this architecture. And for the prediction and the bite-size similarity function, it also does experiment. Prediction is also very.
So this is a Boya paper, right?
No, it's from the simple Siamese.
Simple zero.
Yeah, simple Siamese. Because he want to say that just use a simple stop gradient, it works. Okay, so
the stop gradients, the stop gradients, and there's no momentum.
yeah, no momentum, just the stop gradients, it works.
Why? I didn't get it. So any intuitive explanation for that?
Yeah, it's in the later. So he also experiment on the prediction. It shows that prediction part is also very important. So we answer, he first do the experiment. So we just from the result, we can see that predictor is important part of the neural network. And the batch size and the similarity is not important. Okay, so after the experiment, he also compared to the BYOL, and it says that the momentum is not important because he didn't use the momentum, but the result is also very good. I think for the momentum method, the stop gradient is the most important thing. So no need to add a more momentum architecture or mechanism in the in this architecture in the Siamese network. And then compared to CMCLR, because he can't very easy to compare with CMCLR because the CMCLR used a negative sample. It compares the dissimilarity of the model. So he just said it's different from the constructive learning problem. So he just didn't compare with it. So after the experiment and the comparison, it said the stop gradient and the predictor is very important, and the batch size and similarity function is not such important part. So he put forward a hypothesis to explain these things, and he said simple Siamese is actually an implementation of expectation maximization algorithm. So now we just have a short review of the, I think you all know and the time limit, so we just skip this part. Anyone have question on the expectation and the maximization task? You can just review the k-means algorithm. It has 2 steps, and one is expectation and one is maximization. So so let's look how the hypothesis like. First, we consider a loss function of the following form, and this f is actually the representation part, like ResNet, and the t or tau is just the augmentation part. And the expectation, could you understand this formula? The eta x is also a representation of x. He just first define a loss function and said, oh, this loss function is similar to Siamese loss function. So he also analyzed the expectation maximization algorithm.
Can I regard f is a projection or is a prediction, and tau is tau is encoder.
Yeah.
Tau is one encoders and eta.
And the f is the encoder.
Actually, what about eta?
Eta, actually, this is very difficult to understand. He said eta is another set of variables. You can see that he also said that eta is actually a representation of x. So here eta x is like the true representation of the picture, and the f is the network, so is the representation output by the network.
Okay, let's skip these ones. Let's skip these ones. Let's see what do you have in the next slides.
Okay, so now we want to minimize the loss of this function. Actually, it is very similar to k-means casting. You can regard the theta. Actually, the theta is the variable of the network. So here, for the k-means, you can just think theta is the clustering centers, and it is the learnable parameter. And the variable eta is the assignment vector of the sample x.
Okay, let's skip these ones. What is the takeaway?
What do you mean?
Takeaway is conclusion. What's the conclusion here?
Conclusion is just that they think that the Siamese has the Siamese network is actually a kind of expectation and maximization algorithm.
But every deep learning model is expectation maximization algorithms. And what's the specific part?
I don't know, actually. I don't know all the neural network is a explanation of expectation maximization algorithm.
Keep going on. So I think I get very little information here. So the problem is that they proposed a new Siamese model. In this Siamese model, they achieve better results with less requirement.
Oh no, he just simplified the Siamese model of the because the BYO is too complex and the CMCR is too complex. He just want a simple one. And why the simple one also works? He said there's a hypothesis called the Siamese is also a
okay. So that's the end approach, right?
What?
That is the end of talk.
Yeah. It is end of the talk. And there are also some questions like the batch normalization, batch size we didn't talk about, and the negative samples we also didn't talk about. They are also very, you know, because in our other neural network model, we don't very emphasize on the batch size or the like negative samples. But for this model, it's a very important part. And
okay, so let me ask. So there's less people here. I'm going to clarify whether you really understand. So maybe I ask questions. What is model collapse?
Model collapse means that the model has the same output for any input. Could you?
And why Siamese model will have model collapse?
Because if you let the two networks share the same weight, you know, if you let I just give you the picture. If you let the two encoder have the same weight, then it will output the same representation. Then the similarity is the max.
But the problem with Siamese model is not to input it itself, not input it. It will actually compare two different images. So
yeah. You compare to different images, and you want to minimize the distance of the different augmentation picture. So if the encoder has the same parameter, then for different augmentation picture, they also input the same representation. So if the model collapse, that means for all data augmentation for all pictures, they all input the same representation.
And how the problem addresses model collapse?
You use the stop gradient.
Stop gradients. And let me be more specific about the stop gradients. And for no.
Yeah, he so why stop gradient prevent more collapse? He also didn't have a conclusion. He said it's a future research part.
Maybe more specific. Let me ask more specific question of the slope gradients.
Okay.
Give me a picture of the slope gradients.
Yeah.
So here, giving the online output, and theta and I don't know how to pronounce it. Sigma.
That's just
Right? What?
epsilon.
Epsilon. Okay, sigma and epsilon. And they share different weights, right?
Yeah.
They share different weights, and it have a prediction.
For this BYOL, they share different weights, but for the simple Siamese, they share the same weight.
Okay, if they share this, whatever. So let's talk about the slope gradients.
Okay.
And when we have the slope gradients, it's going to do the back, and it will apply backward propagations for the online branch, right? For the sigma, for the theta, for the theta part, it will update it on online branch, updated the weights, back propagated weights, or updated weights with back propagation, right?
Yeah.
And but you can see it still have a epsilon, right? It will still have epsilon. So that means if we update the gradients on the target branch, the loss will still be propagated back on this branch there. Am I right? Hello?
I don't think so. You just
If you don't think, okay, so that means the weights there. So that means from the very beginning, the epsilon, from the very beginning, the epsilon is just initialized weights, right?
Yeah.
And this initialized weights just using a momentum means it partially update the weights on the theta or the online branch.
Yeah. But I think it's not a part of the slope gradients. Slope gradients is just make the two neural net have different output. I think.
But they should make it similar, right? So this is the one to be minimized.
Yeah.
And as far as I learned, the slope gradients is just a stop updated gradients on one branch.
Yeah.
Or stop updating the gradients in one branch through back propagation. It is still somehow updated gradients, but it's not. Okay, let me ask another question. If for the simple Siamese, both the online and target branch share exactly the same branch.
Both the online and tagged have the same parameter.
And for simple Siamese.
Yeah.
And if that is the case, they will definitely be different, right? So suppose it was output of vectors, and for the Qs will be apply operation and get the output, right?
Yeah.
Because they share the same, and they would like to minimize the distance like this. So we just need to learn a Q. We just need to learn a Q network. For example, it is how to say it? It is a unit matrix, like 1, 1, 1, 1, etc. And z times this matrix will just be itself. And it can still maximize the loss or minimize the loss.
Yeah.
So isn't it weird? Very strange, right?
A bit strange. Yeah. After you say it, I can share the algorithm. You can see the algorithm here. It compares the loss of the one is projection, another is prediction. And so he computed the loss of two different layers. And one layer, it's just a detached stop gradient. The Z layer, the prediction layer, he stops the gradients here. So he just used this mechanism to stop the gradient.
Let me see. For each x, and to do the augmentation, the x1, x2 will be different, right?
Yeah.
And they will be different. Then it will have z1 and z2. But these f and h are exactly the same.
Yeah. F is the projection, that means the encoder, and then you get the Z1, Z2, and then you predict each. But the Z1, Z2 is detached with the gradient.
Both z are detached.
Yeah, because it use the you know the converse.
Well, let me read it out.
Yeah.
And somehow P and P1 and Z2 and P2 and Z1. So somehow the prediction will be same. Branch there will be a predictor and there always be the same amount. Detach. If it detach from Z, D, okay, the D is actually so apply stop gradients is just updated. So okay, so it's just updated encoders, and because all the encoders both branch share the same encoders, so it's somehow. Let me think about it during the presentation, and it apply. I think that stop gradients actually makes prevent the model collapse because it somehow will learn the very different presentations even from F, right?
Yeah, it's actually like the EM algorithm. It's just fix one thing and change another thing and automate another thing and then just converse. You can see that for the first round, the X1 gets the P1 and the Z1, and for the another encoder, it gets the P2.
Okay, so let me.
So they compare the Z1 and the P2 here. Oh, P1 and Z1, and here is the P2. So he compares the Z1 and the P2. And then he converts the input. Here he gets the P2 and the Z2. Use a different color. P2, P2, and Z2.
If it's a P. I think the predictor here is more like to, but how does it compare to? But in this case, if we have two input x1 and x2, right? So if we fit into network, we have the similarity of x1, x2, and whether they will be the same. X2 and x1. Right.
He just, I said he just added them. Added them. He just.
I know that it's a loss function. It's a loss function, but I'm saying that how do we deploy the model in the real world?
Oh, what's your meaning?
I'm not saying training. I'm saying prediction.
Prediction.
Yeah, and for example, I have two phases. I would like to know whether these two phases belong to the same people and how to use your Siamese architecture.
It's a self-supervised. So he just used the representation. He used the encoder part. He not this. What you just
What I mean is that, yes, I do have the representation and using cosine to compare the similarity of the representation. Is that okay?
Yeah, okay.
So I'm saying that if I feed it to focus on x1 is the phase 1, x2 is the phase 2, and we feed those images into the model. Can we understand this? And
Yeah.
we will get their similarity by computing the cosine similarity. You understand this?
Yeah.
Okay, so my question is, when we feed it, if we switch the order of two images, will they get the same result?
Yes, because the encoder is the same.
I'm saying that whether the predictor will be involved into prediction. You're right, because this one branch have a predictor. So I'm asking whether Siamese x1, x2 is equal to Siamese x2, x1. By right, they're supposed to be different, right?
If you use this architecture, maybe it's different.
But it's definitely different because we call it f, because in encode f will output the vector, and for any branches is
Yeah. But this architecture is not used for this task.
they're used for what task?
It is used for training the encoder.
Yes, then or training the encoder. And
Yeah.
after the encoders, we just using the encoder to do the Siamese model.
Yeah, you just you not use the predictor, you just check the, you can just check the cosine similarity of the representation. So you just have the encoder and check the representation similarity. So for this architecture is used to train the encoder.
And the goal of the predictor is just to
You mean this part?
yeah, just for the model collapse, right? Just for model collapse.
Just to map the map the different space.
Okay, thanks. I think let's call it a day. And thanks for your presentations. And I think I need to digest this a little bit later.
If you if you have a question about the predictor, actually it has some explanations on the why use the predictor. Yeah.
Okay. Okay, thanks, Yufan. Let's call it a day.